Okay, let's talk about analyzing process performance. So a key idea that we need to understand when we want to look at any process is the idea of a bottleneck. A bottleneck is a special type of constraint. A constraint is any factor that limits the performance of a system and restricts its output. Okay? So the bottleneck is the constraint which is affecting the system because it is stricter or narrower than any other constraint. So a bottleneck is a constraint whose available capacity limits the output of a process. In other words, the slowest step in the process or the step with the lowest capacity. So if you look at this pipe, there's a bottleneck. It's less wide in the middle. And so if you put in fluid that fills up this part of the pipe, right, this part of the pipe, then not all of the fluid that's getting pumped in from here can pass through the narrow bottlenecks. Only the amount which is the bottleneck can carry will pass through. So what will happen after the bottleneck? The pipe will not be full of the fluid, whereas it will be full of the fluid on this stage. So the bottleneck will restrict how much fluid can pass through. Okay. So how does that happen? To understand the effect of a bottleneck, we need to understand certain concepts, specifically the concepts of blocking and starvation. So we're going to understand starvation and blocking by looking at this simple process. So we have one worker at each station. We have three tasks. Task A done at the first station, which takes 3 minutes per unit to complete. Then we move to task B. That's the next in sequence. That takes 5 minutes per unit. And then we move to task C, which takes 2 minutes per unit. So the first question we need to ask ourselves is, what is the bottleneck? If you recall the previous slide, we said bottleneck is the slowest part of the system, i.e. the part with the lowest capacity. But slow here means how many units it can give out per unit time. If its capacity is low, it's going to produce or give out fewer units per unit time. So when we look at these times, 3 minutes per unit, 5 minutes per unit, 2 minutes per unit, these are called cycle times. Cycle time is the time it takes to process one unit. Okay? So which one is the slowest? Well, the slowest one should take the longest time per unit because it has the lowest capacity. So task B takes the most amount of time per unit. So this is the slowest or the one with the least capacity. Then after that is task A, which is speedier, has more capacity than B, but it's not the fastest. The fastest is task C because it takes the least amount of time per unit. Okay? So our bottleneck is task B. Now, at the bottom of the slide, I have a time diagram drawn. Okay. So let's say at a certain time, we start observing this process. So at this time, if this was the start of the day, then when the first unit flows into task A, task B and C would have nothing to work on because they just started the day empty, assuming they didn't carry forward any work from the previous day, any work in process stuff. Okay. Usually that's not the case in manufacturing. Usually there might be at least one unit here right before task B as a work in process unit when task B closes at the end of a shift. So the next day when task B starts up, there'll be one unit here waiting for it to process. Okay. So whether there was a unit here or not, if not, then after a time, this pipeline would become full. because once task A finishes something, it'll pass it on to task B. When task B finishes with that unit, it'll pass it on to task C. So after a while, all three will be working on something. So that's what I've captured here, that task A is working on part 10, task B is working on part 9 or product 9 or unit 9, task C is working on unit 8. Okay, so they're all working on something. Now they all take different times. So after 3 minutes are up, well, the first one to finish will be task C. So after 2 minutes are up, task C is done. Okay, with P8 at this time right here. Okay. Now, task C cannot start right away on P9 because task B is still working on P9. Task B has to finish with P9 for P9 to go to task C. But because the previous task is taking longer, task C is going to sit idle until task B finishes P9, and that happens after 5 minutes. Okay, so of this 5-minute time window that we observed here, task C only gets to work 2 out of the 5 minutes, then it's done, and now it has to wait for task B to get done with P9 before it will get P9 to work on P9 once it's done with P8. Okay. So this waiting for more input to work on is called starvation. You're waiting for product, for units, for customers to process because you got done quickly, but the previous station is not done, so you have to wait for the previous station, and then once they're done, then you can start. Now let's look at task A. Now task A is also faster than task B because task B is the bottleneck, has to be the slowest. If task A gets done after 3 minutes, at this time after 3 minutes, it cannot pass on the finished P10, finished from task A, but still needing task B and C to be done to it. It can't pass on P10 to task B because B is busy. B doesn't have space, it's working on P9. When P9 goes out of task B, it will be ready to accept the next product, and then task A can pass on P10 to task B, right? This is assuming we don't have any in-between storage space. Sometimes you can put like a shelf here for work in process inventory to be stored here, and then task A could put P10 into that shelf or cart or some storage device and get started on the next item. But here we have not put in any triangles for work in process inventory symbols. So we're assuming these are like working stations. There's no place to put any inventory. When task A is done, it gives its piece to the next task. This is very common in assembly lines. In assembly lines, between two people working on the assembly line, there's no really work in process storage area. We could store up a lot of the work in process inventory. People are close to each other and the line is flowing. So if task B is not done, task A would not be able to push its product here. Not all assembly lines are self-paced where the assembly line is just running. Some assembly lines are just like a long table where you push your unit to the next person when you're done with your unit. Okay. So imagine sometimes, let's say you are planning a birthday party or something like that, and you are making these bags, goodie bags. So you have 3-4 different types of candy or toys, and you line up your kids or you line up your friends, and you take a goodie bag, you put in a candy, you pass it to the next person puts in a good candy or something in the goodie bag, passes to the next person. When they're done with the line, the goodie bag is full of all the candy and toys you want to put into it, and then you put it down and so on. And this assembly line, you keep passing on goodie bag. You do your job, passing the goodie bag, right? Now, let's say you put your candy quickly into the goodie bag, but the person to your right, they are still working on their goodie bag. Now, what do? You have to wait for them. Assuming there's not a lot of place to pile up goodie bags between you two, right? So once they're done, then you pass on the goodie bag to them, and then you start on the next goodie bag. So this here, task A is experiencing what we call blocking. It's being blocked by task B for 2 minutes until task B is done, and then it can pass on P10 to task B and start working on P11. So blocking is when you're waiting for the next person or task in line to finish. Starvation is when you're waiting on the previous tasks to finish. Because in starvation, you're waiting on the previous station to get done and send you the stuff. Blocking, you're waiting on the next station to get done so you can send them your stuff. So that's the idea of blocking and starvation. And so you can understand this idea when there's no way to store things in the middle. But you might say, that's unrealistic. You know, if we are filling up these goodie bags and the person after me is slow, I can just put my goodie bags in between us. There must be some space, and I start piling up goodie bags between us. Now, let's say you have thousands of goodie bags. After a while, let's say you've piled up 50 goodie bags between you and the next person, you're going to have to stop. And the reason that pile is going to grow is because you are doing work faster than the next person. So as time goes on, you're going to complete more and more goodie bags on top of what the next person is doing. So if you're putting, 5 goodie bags a minute down, the other person is only picking up 2 goodie bags a minute. So every minute you add 3 goodie bags to the pile in between you because you're working at a faster rate. So any extra you produce, the other person can't handle it, right? So even if we allow for work in process inventory, there's still going to be blocking. It's just going to be delayed a bit until the work in process pile fills up. And then once you have those 50 goodie bags there, there's no more room to place the next goodie bag. Things are going to slip and fall and get damaged or something. So you have to stop and wait until the pile goes down. Then you start putting it in again. So work in process inventory is not a solution to blocking. It just delays the blocking to happen because task A can just fill up the work in process inventory. Task B is emptying it more slowly, so the work in process inventory builds up. And at some point, task A will have to stop and wait. And when that pile goes down, again, task A can start putting stuff there, right? So it's either you wait 2 minutes after every unit, or you just keep going for a while and pile up work in process inventory as task A, and then you take a big break, like an half-an-hour break or something, while task B empties that pile or makes it go down halfway or whatever, and then you start piling it up again, right? Same thing for starvation. If there was a work in process pile before task C, after P8, task C would not have to wait. It'll just get something from the work in process pile and start working on the next unit. But because task C is faster than B, it's going to eat up that work in process pile much faster than B can create it. So even if you had a work in process pile before task C, it will only delay the starvation a little bit. After a while, C would be done with the work in process pile, and then C would have to wait again. Okay. So work in process does not solve blocking and starvation. It only delays them. Whenever you have tasks in sequence that have different speeds of working, i.e. their cycle times are different, they take different amounts of time per unit, you're going to end up with situations of blocking and starvation. Okay? Blocking always happens when a faster task precedes a slower task. So you have a faster task, and after that you have a slower task. The faster one will be blocked. Starvation always happens when you have a slow task followed by a faster task. The faster task which comes afterwards will be starved because the slower task can't produce fast enough to feed it. Okay, so this blocking and starvation is what leads us to the most important idea in this lecture, which is that the entire capacity of this process is determined by the capacity of the bottleneck. Okay, let's write down the capacities. So let's do capacity per hour. So how much can task A produce in 1 hour? Well, 1 hour is 60 minutes. Every 3 minutes we produce a unit. So 60 over 3 would give me 20 units per hour. Okay, that's the capacity of task A. Okay, task B capacity is going to be 60 over 5, which is 12 units per hour. And task C capacity is going to be 60 over 2, or 30 units per hour. And this is very standard. You take the cycle time, you do 1 over the cycle time times, if you need if you want to do capacity per hour, you'll multiply it by 60 minutes per hour, because cycle time is in minutes. You have to convert from minutes to hours. Or if you want to do it by day, you'll do, okay, there are 8 hours in a day, 60 minutes in an hour, 480 minutes in a day. 480 divided by the cycle time will give you the capacity per day, right? Now, task A has a capacity of 20. Task B has a capacity of 12. Task C has a capacity of 30, but the total process capacity is going to be this one, 12 units per hour. This entire process can only give you 12 units per hour in steady state. If you have lots of WIP in front of C in the beginning, it may give you more than 12 per hour, but as that WIP is eaten up, you'll go back to 12 units per hour. So in steady state, in the long run, the process capacity equals the capacity of the bottleneck. Why? Because of blocking and starvation. Okay. So hopefully it makes sense. If not, think about it. Maybe you could get 3 people together. One is task A, tell them to spend 3 seconds on doing something with a paper, and you spend 5 seconds doing something with a paper. The next person spends 2 seconds doing something with a paper, like folding it or whatever, being in paper aeroplane, and then run that assembly line operation with a stack of papers, and you can observe how much you can produce per hour, and you'll notice that the bottleneck will be, the bottleneck's task's capacity will be the capacity of the whole process. Okay. So this is a very important idea, blocking and starvation. It explains the reason why bottleneck limits the whole process. Okay, so let me... Okay, so you can see the capacities here. And let me identify the bottleneck. We did already task B. Highest processing time, lowest capacity. Okay, blocking illustrated, starvation illustrated, and hopefully, hopefully you understood the ideas on this slide. So, in conclusion, the key to assessing the capacity of a process is identifying the bottleneck, because the capacity of the entire process equals capacity of the bottleneck. So how can we identify the bottleneck? It is the step with the lowest capacity. So if you calculate capacity of each individual step by doing, 1 over the cycle time, as you'll see later on, we'll calculate capacity again, do other examples. You do 1 over cycle time, then you multiply by 60 minutes per hour to convert from minutes to hours. If you want to do capacity per hour, if you want to keep capacity per minute, it's just going to be 1 over the cycle time. So you can see the one with the lowest capacity is the bottleneck. Utilization, the step with the highest utilization is the bottleneck. If you look at this diagram, notice that task B has no idle time. It's working through and through. P9, then P10, then P11, then P12. There's no free time for task B. Its utilization is 100%. Whereas task A and task B have less than 100% utilization because they get this free time when they're blocked or starved. They're not doing anything. Okay, so bottleneck will be the step with the highest utilization. Now, if we tell a task to continue producing and build a pile of WIP, we'll see that the bottleneck will often have the largest amount of work in process inventory before it, because things will get piled up and it'll not be able to remove them fast enough. After the bottleneck, things will not get piled up, because after the bottleneck, everything that comes after it is faster than the bottleneck by definition. Otherwise, this wouldn't be the bottleneck. So whatever the bottleneck gives out, the tasks downstream can handle that, and they clear it out. So there's no buildup of WIP after the bottleneck. Before the bottleneck, you'll see that often the WIP will be the highest before the bottleneck. Bottleneck task causes all other tasks to have idle time, as we talked about it, because of blocking and starvation. there could be, for example, here, let's say that task C also took 5 minutes per unit. Then task B and C would both be bottlenecks because they would both be the slowest tasks in the sequence. Okay, so the bottleneck doesn't have to be 1. It is usually 1, which is the slowest part of the process. But if 2 parts are equally slow and they're the slowest, then both of them are the bottleneck. Okay, now we're going to talk about some metrics to analyze our processes using this simple example of a simple sequential process with task A, task B, task C, task D. The cycle times are given here. We're going to talk about cycle time, capacity, utilization, and throughput time. Okay, so let's continue. What is the cycle time? It is the average time between the completion of successive units of product, or in the case of a service process, the average time between departures of successive customers. So cycle time is usually we talk about a particular step of the process or a task or a workstation to define the cycle time. So if there was only task A, let's imagine there's no task B, C, and D, and we were to stand at the end of task A, what will be the time between a unit coming out of task A and then a second unit coming out of task A? It'll be 2 minutes because it takes 2 minutes per unit, right? Every 2 minutes, task A can throw out the next product or unit that's been processed. If there's no starvation, no blocking, this task A can run by itself independently. So that's the cycle time. Same thing for task B. If there's no task A or task C or task D, just task B by itself running independently, so there's no starvation, no blocking, then task B can spit out or send out a product every 4 minutes because it takes 4 minutes to process 1 unit, right? So that's the cycle time. If there's customers flowing through, then every 4 minutes task B can finish working on a customer. The cycle time is 4 minutes. Okay. Now you can also define a cycle time for the entire process. How? You can stand here at the end with a stopwatch and let the whole process run. If the process starts with just empty, there's nothing in the process in the morning, you let it get to steady state, wait a while, then you stand here with a stopwatch. Once 1 unit comes out, you start the stopwatch. Then when the next unit comes out, you stop the stopwatch, and the time between them will be cycle time for the whole process. The cycle time for the whole process will be the cycle time of the bottleneck. Why? Because we know that cycle time is linked to capacity. It is another way of representing capacity, because capacity is 1 over cycle time and cycle time is 1 over capacity, right? It's just the inverse of the capacity. So if the capacity of the entire process is limited by the bottleneck's capacity, then the cycle time of the entire process will also be limited by the cycle time of the bottleneck. You can think of it, if you go back to this picture, okay, imagine if you stand at the end of task C, you can notice that even though task C takes only 2 minutes, because of starvation, it has to wait 3 minutes for the next item. So if it sends out a unit here and you start the stopwatch, it's waiting 3 minutes to get the next item from task B. Then it's going to spend 2 minutes on that next item. So the next item will come out after 5 minutes. Excuse me. So the cycle time of task B will show up at the end of the process because of starvation and blocking. So remember when we talk about the cycle time of individual tasks, okay, we assume there's no starvation and blocking and we run the individual task independently. So there's no starvation and blocking, and we measure the cycle time of an individual task or workstation or worker. But when we talk about the whole process, then the cycle time of the whole process, you have to let the whole process run, and the cycle time will be affected by the bottleneck. And the cycle time of the whole process is the cycle time of the bottleneck. Okay, so these times here, the time each task takes or each step takes per unit, that is the cycle time. Okay, almost always the cycle time is given to you, and you have to use the cycle time to compute the other metrics. But if the capacity is given to you, then 1 over capacity will be the cycle time. Okay. Remember that when you do capacity is 1 over cycle time or cycle time is 1 over capacity, the units of both will be the same in terms of time. So let's say if the cycle time is 5 minutes, then the capacity will be 1 over 5 units per minute. Okay, which means 0.2 units are produced every minute. That's the capacity. Now, usually we don't like to talk about capacity per minute because, we like to make sense of things per day, per hour, per week. So then you have to multiply by whatever constant you need to convert capacity from units per minute to units per hour. So 1 hour is 60 minutes, so multiplied by 60 to get 0.2 times 60 will be 12 units per hour. And if you want to do per day and a day has 8 hour working time, you'll do 12 times 8. That'll be units per day. If you do it per week, it'll be 12 times 8 units per day times 5 working days a week. That'll be units per week. So you can then multiply by constants to convert the unit of capacity from units per minute to units per hour or units per day. Okay, but the actual formula is just 1 over cycle time, where the units are kept. So if cycle time is in minutes, capacity will be units per minute. If cycle time is in seconds, capacity will be units per second. Okay. So again, just showing you that the process cycle time is determined by the bottleneck. And these are the individual cycle times of each task. The capacity is the maximum rate of output of anything that you're looking at. So if you're looking at task A, capacity of task A will be the maximum rate of output of just task A running independently without starvation or blocking. When you talk about the whole process, then obviously the starvation and blocking happens, and then you look at the bottleneck. So let's calculate the capacity of each of these tasks. So the capacity of task A is just 1 over cycle time, or half units per minute, but usually we don't like to talk about capacity in units per minute. So if you want to talk about capacity in units per hour, we multiply the capacity of half by 60 minutes in an hour, so we get 30 units per hour. This is 1 over 4 times 60, or 15 units per hour. This is 1 over 5 times 60, or 12 units per hour. And this is 1 over 3 times 60, which is 20 units per hour. These are the individual capacities, and then the capacity of the whole system will be the capacity of the bottleneck. So hopefully you can understand the difference between capacity and cycle time for one task by itself running independently versus the capacity and cycle time of the whole process. Okay, let's look at utilization. So utilization is the fraction of a resource's capacity that is actually used. It is also, you can think of it as the useful time, namely the time spent working on something, as a percentage of the total time available. So if utilization of a resource is 80%, then it means the resource was being used 80% of the time, and 20% of the time the resource was idle. So we're going to look at a couple of ways to calculate utilization. The first one is you can look at capacity. So you can look at the actual capacity, actual output, how much did it actually produce, divided by the capacity, which is the maximum output possible, and this ratio would give you the utilization. Okay. So let's do this. So what's the utilization of task A? Well, if you look back, okay, this process is going to run at the bottleneck speed, task C. So the actual output of the whole process, because of blocking and starvation, is going to be 12 units per hour. But task A could have produced 30 units per hour. So 12 over 30 is the percentage of time task A is busy, and the remaining time task A is just being blocked and waiting for other tasks to get a move on. Okay. So the utilization of task A is the output, which is determined by the bottleneck. Remember, the output of a process is going to be determined by the bottleneck speed. And because of blocking, task A can't go faster than 12 units per hour. If it did, it'll just build VIP, and eventually it'll have to stop. And the capacity of task A was 30, so 12 over 30 is 40%. Task B's utilization, again, task B is going to be blocked by task C, so it can't go faster than 12 units per hour. And it could have gone up to 15 units per hour because the cycle time is 4 minutes. So 12 over 15 or 80% is the utilization of task B. The utilization of the bottleneck is 100% because the output of the process is limited by the bottleneck to 12 units per hour. The bottleneck's individual capacity is also 12 units per hour. So the bottleneck runs on 100% utilization. It never is idle. Utilization of task D is, again, the output, the actual output of the process is being limited by the bottleneck. So the actual output is going to be 12 units per hour, limited by task C's capacity. But task D's individual capacity is 20. So 12 over 20 or 60% utilization for task D. Now, what if we didn't have a lot of things to work upon, and our demand, what's coming into these tasks, okay, or our demand, what we have to produce, is less than the bottleneck's capacity. So bottleneck can produce up to 12 units per hour, but let's say it's a slow day, not many customers coming, and we only need to go at 6 units per hour. In that case, the actual output will be limited by the low demand and we'll be producing 6 units per hour. And then you will take 6 instead of 12 and calculate the utilizations. Because even though the bottleneck's limit is 12, your demand is so low that day that you're actually running even less. And then your utilization is low not because of the bottleneck, but your utilization is going to be low everywhere because you just don't have enough demand to run the process all out. This utilization that we calculate is if you run the process all out. So either you're doing a batch production, you're running the whole process on a batch of goods, or your demand is equal to the bottleneck's capacity, 12 units per hour or more, and you're trying to catch up with demand and you're running all out. So if you're running all out, you'll be limited by the bottleneck speed of 12 units per hour, and these will be your utilizations. But if your demand or the load on your system is less than 12 units per hour, then even the bottleneck will have idle time. Even this utilization will be less than 100%. And we'll look at an example of that. As I mentioned, cycle time and bottle capacity are just images of each other, mirror images in a way, because one is one over the other. So if we can calculate something using capacity, we can calculate it using cycle time as well. So utilization is also cycle time of of the current task divided by the cycle time of the bottleneck times 100 to get a percentage number, and that'll be the utilization. Let's look at task A. That's 2 minutes. So the utilization of task A will be 2, and the bottleneck cycle time is 5. So 2 over 5, which is 40%. Exact same answer that we got here with the output limited by the bottleneck versus the capacity of task A. 40%. We can do it with cycle time, 40%. Same thing for task B. Cycle time is 4 divided by the bottleneck cycle time, which is 5, gives you 80%. Again, bottleneck gets 100% utilization, and task D gets cycle time of task D divided by the bottleneck cycle time of 5, gives you 60%. Again, this is when you're running the process all out, either because we're processing a big batch or because the load on the system, the demand from the system is equal to or more than the bottleneck, which means equal to or more than 12 units per hour. So we're running the process all out, and then this is what will happen. Task C will run all out. Everybody else will have idle time because of blocking and starvation, and these will be our utilizations. Okay. Now let's look at the case where we don't run the system all out. So the demand is 10 units per hour. We only need to pace our process at 10 units per hour because anything extra is not needed. The demand is low or our output requirements are low. Okay. The reason could be customer demand. The reason could be we already produced too much previously and now we need to produce less. A production plan is calling for lower production, whatever the reason might be. Okay. So here, when we calculate utilization, instead of the bottleneck capacity, which is the limiting output, our output is limited by the low demand or the low load on the system. So we'll use 10 instead of the 12. So task A utilization would be 10 over 30 or 33%. Task B utilization will be 10 over 15. Again, 15 is the capacity of task B. How? 60 minutes per hour divided by 4 minutes per unit gives you 15 units per hour. So that's task B's capacity at the bottom, the load on the system at the top. Why 10 and not 12? Because we're running it slower than the bottleneck speed, the speed of the bottleneck, because there's less demand on the system. So 10 over 15, 66.67%. Task C utilization is 10, which is the actual output, over 12, what's possible for task C to achieve, the capacity of task C 12, and we get 83%. Notice here that the bottleneck is running at less than 100% utilization. Why? Because the demand is lower than what the bottleneck can produce. So the load on the system is even less than the bottleneck's speed. So bottleneck is going to have some idle time too now. Okay, and then task D is going to be actual output we need to produce is 10 units per hour. Task D can handle up to 20 units per hour. So task D's utilization is 10 over 20 or 50%. So if the question specifies a demand which is less than the bottleneck's ability to handle, bottleneck's speed or capacity is higher than the demand, then you'll use the demand as the limiting factor and calculate utilization. But if the question does not talk about demand at all or the load on the system at all, then you'll just do what you did before and you'll use the cycle time formula or the capacity formula and use the capacity of the bottleneck as the limiting factor. Okay. So slide 18 and 19 give you two ways to calculate utilization when you're not given the demand or the load on the system. So you assume you run the system all out, like doing like processing a big batch or something like that. But if you're given the demand, then you'll use the demand as the limiting factor if the demand is less than the bottleneck. What if you're given the demand and the demand here was 20 units per hour? Then again, the limiting factor will be the bottleneck and the actual output will be 12 units per hour. So instead of 10, you'll use bottleneck capacity of 12. It'll be 12 over 30, 12 over 15, 12 over 12, 12 over 20. Because you can never go above the bottleneck speed. So if the demand is less than the bottleneck, we use the demand. If the demand is not given or the demand is equal or more than the bottleneck, then we use the bottleneck as a limiting factor in our utilization calculations. Okay. So hope that's not too complicated, but I think when you do some examples or work through some examples, you'll be fine. Now let's look at throughput time. It's a very important idea. Throughput time is the total time a unit spends in the process. So the way to think about it is this. Let's say you have a unit that is marked. It has a label on it so you can track it through the system. Okay. When this labeled unit, it has a flag on it or some red ribbon around it or whatever. When this enters your system, you turn on the stopwatch. Ding, start. It makes its way through the system. When it pops out on the other end, you stop the stopwatch. The time on your stopwatch is the throughput time, which is the total time this one unit spent in the system. Okay. This is very important because let's say you have a service process. Throughput time tells you the total time the customer is going to spend in your process. Okay. Okay. So the way we get throughput time is we just follow this unit that entered here and keep adding all the time it takes until it gets out. So when this unit, which is marked with a red ribbon or a flag, it enters here, task A is going to spend 2 minutes on it. Okay. Then it's going to maybe wait here because of blocking or whatever. So we add the waiting time. Then task B is going to spend 4 minutes. Then it might wait here again because of blocking. Then task C is going to spend 5 minutes. Then it's going to wait here. Then it may not wait here because there's no blocking here. And then it's going to spend 3 minutes. It's going to go out. So it's going to be 2 plus 4 plus 5 plus 3 plus a bunch of waiting times added up. Okay. So that's the throughput time. Now, how much waiting time there is, it's not just based on blocking. If you have inventory here, like work in process inventory, it's going to go into the work in process pile and it might be there for days. It depends on how big work in process inventory piles you have. If you have a lot of inventory in your system, which is why people don't like a lot of work in process inventory, right? If you have a lot of inventory in your system, that unit is going to spend a lot of time waiting in that pile of work in process inventory before the next task takes care of it. So sometimes the throughput time is huge, and majority of the throughput time, 80-90%, is just waiting time, waiting in work in process queues. Okay. So here we'll do 2 plus 4 plus 5 plus 3 plus any waiting times that we have. So it's going to be 14 minutes plus waiting time. Now, because we usually don't know the inventory, the work in process inventory policy, how much space they have, how much inventory they're going to have. So I'm not going to ask you to calculate the waiting time. So for the purposes of this course, all you do is you add up all the cycle times where the unit flows through. So it flows through task A, you add the cycle time of task A, which is 2. It flows through task B, you add the cycle time of task B, which is 4. Flows through task C, you add the cycle time. Flows through task D, you add the cycle time. So you get the lower type bound on the throughput time. The throughput time can't be less than 14 minutes. It's going to be more plus waiting time, but we don't know the waiting time, so we're just going to say it's 14 minutes, the lower bound, okay? So that's what you'll have to be asked to calculate. What's the throughput time? Just add up the cycle times. Don't worry about the waiting time, although wait time is going to be there in reality, but calculating that becomes more complex. A lot of times people will use simulation to get an estimate of the waiting time. Okay, so when we are not doing a simulation, we're not going to worry about the waiting time. We're just going to add up the cycle times like this and say 14 minutes is the throughput time. Obviously, the real throughput time will be more because there'll be waiting time involved as well. Okay, so if I don't provide you the waiting time, then you're just going to give me this 14 minutes. Okay, but if I tell you, okay, waiting time here is 5 minutes, here is 20 minutes, here is 0, then you just add up the waiting times as well to 14 minutes to give me the answer. Okay, now we're going to look at labor utilization, the average utilization of workers in these tasks for the whole process. Okay, so remember we already calculated utilization up here for each task. That is the utilization of the worker or any resource you're using in task A, task B, task C, task D. So task A utilization is 33% and so on, right? Depending on the demand and so forth. Now we want to get an overall idea that in this whole process, what is the average utilization for our workers? Okay. So what we do, okay, is we can do it two ways. The easier way is using the cycle time, the bottom formula. You add up all the cycle times at the top, okay, and then you divide by the cycle time of the bottleneck multiplied by the number of stations you have. The 4 stations or 4 tasks. So a task could have multiple workers, so you don't worry about the workers per se. You're just going to look at the effective cycle time of the task, okay, of the bottleneck task, and then times the number of steps you have in your process or number of workstations or tasks you have. So it's going to be 4 tasks times 5 minutes cycle time of the bottleneck. At the bottom, there's going to be 20, and at the top is going to be the sum of the cycle time, which is 14. So every 20 minutes, basically, people have worked for 14 minutes. Okay, because of starvation and blocking, some of them can't work the whole 5 minutes every time 5 minutes elapses. So the overall utilization of our workers in this process is 70% labor utilization. You could also call it resource utilization if you have machines working here. So there's nothing special about the term labor here. It's just the utilization of your resources based on the cycle times and the cycle time of the bottleneck. Okay, this just averages everything out for the whole process. Okay. The other way to calculate is to look at how much time each task is going to work in an hour. So you take the capacity of the whole process, which is the capacity of the bottleneck, which is 12 per hour, 60 over 5. Okay, that's the pace at which the whole process is going to work. So to make 12 units or to process 12 units, task A is going to work for 2 minutes per unit. So it's going to work for 24 minutes of the hour, 12 times 2, because you only need to process 12 units for the whole hour. So 12 times 2, 24 minutes, and task A is done. Task B is going to work to process those 12 units, 4 minutes per unit. So 12 times 4, 48 minutes of the hour, task B is going to be working for. And task C is going to be working for the whole hour. There's no break for task C because it's the bottleneck task, right? So every unit, it works 5 minutes. To produce 12 units, it's going to work for 12 times 5, 60 minutes, the whole hour. Task D takes 3 minutes per unit, and to produce 12 units, it's going to work for 12 times 3. It's going to work for 36 minutes to produce the 12 units required in the hour. And so these are the times that each task works for. So you do 24 plus 48 plus 60 plus 36. Now you divide that by 4 times 60, not just 60, not just 1 hour. Why? Because each of them had 1 hour. If you have 4 workers here in this process, you have 4 labor hours. 1 hour by worker 1, 1 hour by worker 2. Because imagine how much wages you'll pay. You'll pay worker 1 the wages for 1 hour, worker B the wages for 1 hour, worker C the wages for 1 hour, worker D the wages for 1 hour. So you'll pay 4 hours of labor wages, right? So it's not 1 hour. You have to divide by 4 times 60 because you have 4 tasks, and each task had 60 minutes, out of which it didn't work for all the 60 minutes, but it worked enough time to produce 12 units, right? Which is the capacity of the whole task, the whole process. So you add up the time each task worked for in the hour. You divide by the 60 minutes per hour times 4 steps, and you get 70% the same answer as this. So you could do it either way. So if I ask you for like the resource utilization or labor utilization of the whole process at the level of the process, you'll do this. If I ask you for the utilization for individual tasks, right, then you'll do this. If demand is not given, and if demand is given, you'll do this. Okay. So you have to be careful with utilization. Are you being asked utilization of each individual task or station? Then you do what we already covered before. If you're being asked for the utilization or the resource or labor utilization of the whole process, then you do what's on slide 22. This is at the whole level of the whole process. So to summarize, for this process, for each task, we have the cycle time written down. We convert the cycle time to capacity. 60 over 2 is 30, 60 over 4 is 15, like that. And then utilization at bottleneck pacing, which is the pace is 12 units per hour, which is this bottleneck speed of the bottleneck task. At that pacing, this will be a utilization. Obviously, if demand is lower than 12 units per hour, then you'll use demand, and the utilization of all of them will be even lower, right? But at bottleneck pacing, this is the utilization, and this is the utilization you'll calculate. If I don't give you the demand, I just give you cycle times and say calculate the utilization of each task. This is what you'll give me. And if I tell you to calculate the utilization of the whole process, then you'll give me this number, which is 70%. Okay. Okay. Now let's get to improving capacity, seeing how we can do. Let's say, we were not happy with 12 units per hour of capacity, which is limited by the bottleneck. What can we do? Well, the first option is add a worker to the bottleneck, because that will reduce the time taken by the bottleneck to process a unit. The bottleneck becomes faster, something else becomes the bottleneck, and so we can produce more. So let's add a worker to bottleneck task C. Because we have 2 workers working on task C, in 5 minutes, we can produce 2 units instead of 1, because each worker is working, right? There's 2 ways it can happen. One is that task C has micro tasks within it. So worker 1 does half of the tasks, worker 2 does half of the tasks, like in parallel. And after 2.5 minutes, they're both done because they have to do half the job. And so if you can split up task C into micro tasks, you can do that. Sometimes you can't split up task C into micro tasks. So what will happen is, task C will take in 2 units at the same time, work on 2 units in parallel. Each worker will work on 2 units. And after 5 minutes, you spit out 2 units. So every 5 minutes, if you output 2 units, then you're on average you're outputting a unit every 2.5 minutes, because every 5 minutes you output 2 units. In other words, your capacity went from 12 units per hour to 24 units per hour. Your capacity doubled. Okay. And you might say, well, how can task C take in 2 units every 5 minutes? Because task B cannot produce 2 units every 5 minutes. You'll have to use some WIP inventory here. Okay, you'll have to have some piled up inventory which can feed task C. And obviously task C is going to get starved eventually because it's no longer the bottleneck, because task B is the bottleneck, because you can't get 2 units every 5 minutes into task C forever, because task B is slower than that. It can't produce that much. Okay, task A can, but task B is like the new bottleneck. If you look at the cycle times, task B is the new bottleneck. So task C is gonna face starvation because it's after the bottleneck. It's a faster task coming after a slower task. Okay. But if you just look at task C by itself without other tasks, if task C was run independently by itself, no starvation, no blocking, task C can give you 24 units per hour or a unit every 2.5 minutes because we doubled the capacity by adding a worker. So what's our new capacity? Well, we have to find the bottleneck because capacity of the process is capacity of the bottleneck. And so the new process capacity is the capacity of task B, which is 15 units per hour. Okay. So adding a worker increase the process capacity from 12 units per hour to 15. So what does this calculation help you do? It shows you the value of an additional worker to this process. Is producing another 3 units per hour worth it to pay an additional worker's wages, right? Do the 3 extra units you produce per hour give you enough profit that is justified to add a worker to get that increase in capacity? You can make that sort of analysis and see if that is worthwhile doing or not. Now, this is a very interesting case where if you look at before we added the worker, we know task C is the bottleneck, right? But if you look at the cycle times, task A and D are much faster than C, right? A is more than twice as fast as C. Takes less than half the time. D is almost twice as fast as C, like a little bit less than twice as fast. But B is pretty slow. It's almost as slow as C. Takes a lot of time. So when you have something like this, where you have 2 tasks, one is the bottleneck and either right next to it or right before it, there's another task which is close to the bottleneck. It's the next bottleneck in waiting. As soon as you add some resources to task C, this is going to become the next bottleneck. Then you can consider the strategy that I'm going to show you on the next slide. This strategy is called adding a cross-trained worker. And you'll see how amazing cross-trained workers can be. So instead of just giving a worker to task C, I'm going to have a worker which is trained to do both B and C. And this worker can split its time between B and C. If they're right next to each other on an assembly line, it can go help C a little bit, then come help B a little bit, then go help C a little bit, then come back help B a little bit. Okay. Again, there are multiple ways to accomplish this. You can look at tasks B and C as a whole, like a 9-minute task. This is 4 minutes plus 5 minutes, a 9-minute task. If it has micro tasks within it, you can split it up at different boundaries than before, and you can give 3 minutes worth of work to this worker, 3 minutes worth of work to this worker, and then the new worker gets 3 minutes worth of work. So the cycle times become 3, 3, 3 for each of the 3 workers. Okay. Or if you can't split up the task as you want, you can't break it into micro tasks, then you just tell this worker, okay, for every 2 minutes you spend at task C, spend a minute at task B. Split your time in this ratio, because if you give 2 minutes to task C, it drops from 5 to 3. And then if you give 1 minute to B, it drops from 4 to 3. So you want to split your time in this ratio 2 to 1 so that both task B and C come down to 3 minutes per unit. If you only give it the time to task C, if you give all your time to task C, you end up in this situation where B is a new bottleneck, which is not that far from C in terms of capacity. And so you just go from 12 to 15, just a little bit bump in capacity. Okay. So if this new worker splits its time in a 2 to 1 ratio, Then what is the new bottleneck? Well, now you have three bottlenecks. B, C, and D are all bottlenecks, and they all have the same cycle time of 3 units. So the capacity of the task is the capacity of the bottleneck, which is 60 minutes per hour, divided by 3 minutes per unit, or 20 units per hour. So notice, adding a trained worker took our capacity from 12 to 20, a much higher increase in capacity than just adding a worker to task C, which took a capacity from 12 to 15. Okay? This is why in some situations, cross-trained workers can be very effective. Now you might be saying, well, what if tasks B and C are not close to each other? So this new worker can't just do 2 minutes here and 1 minute there, 2 minutes there and 1 minute there, because there's maybe some walking time involved. That's fine. All you have to do is you'll have to add WIP, work in process inventory, between these tasks. And then this worker would spend maybe 20 minutes here, then go there, spend 10 minutes, then come back for 20 minutes, then go there at 10 minutes. And the WIP would keep all the stations busy, because when it's spending time at task C is much faster, right? And task B might be building up inventory before it. Then it moves to task B and it speeds that up to drive that inventory pile down, while task C is much slower while it's working in task B. So inventory builds up here, then goes back to C, it drives this pile of inventory down, then it goes back to B, and so on. So if you allow some WIP, you could, even if task B and task C are a little bit far apart, there's some walking time, this worker can spend 2 hours at task C, then do 1 hour at task B, 2 hours here, 1 hour there, or 20 minutes and 10 minutes, or 20 minutes and 10 minutes. So you can do this sort of split in time, even if, you can't switch after every 2 minutes. Then you switch after 20 minutes or switch after 2 hours. But you still give the time in that ratio, and you use WIP to make sure no task is just, waiting for a whole hour with nothing to do type of thing. And use some WIP between in front of task C and in front of task B. And then that would allow you to do this. Okay. Another way to think about a cross-trained worker is that task B and C now have 3 workers and a total time of 9 minutes. So when 3 workers attack a task of 9 minutes, they can finish that in 3 minutes. So task B and C combined became a new task with a cycle time of 3 minutes, with 3 workers working on this task. And so you have task A, 2 minutes per unit, task B and C combined at 3 minutes per unit, and task D at 3 minutes per unit. And then the bottleneck is this and this. They are equally the bottleneck. And then the capacity will be 60 over 3 minutes per unit, or 20 units per hour. So that's another way to think about it. I like this way because it kind of shows you exactly what's happening. This is kind of doing the same thing. It's just saying, well, let's just combine these two. The total amount of labor we need is 9 minutes per unit. And if we have 3 workers, well, we're going to be working at 3 minutes per unit speed or cycle time, because we have 3 workers doing something that takes 9 minutes for 1 worker to do. So 3 workers should be able to do it in 3 minutes. Yeah. Okay. So now let's get to some really important lessons. This is a really important part. So please, if you're tired, pause the video, take a break, stand up. We're almost done with this portion, and I just need to show you the value of what you have learned. Okay. Now, remember when we did all this analysis, right? And we calculate these utilizations. Look at this utilizations we calculated. So even if we run this process all out, it's going to be limited by the bottleneck, and this is the utilizations we'll get. So imagine you are a manager, you come across this process. You see 1 worker at task C working all the time, no idle time. This worker, task C worker, is a hard worker, always working, no idle time. But then you look at worker B at task B, and you say, okay, he's working most of the time. But then you go to task A and you are mad. Like, what is up with worker at task A? This worker is working less than half the time. How can that be right? Any manager, they see a worker working less than half the time, they're going to lose it. They're going to be like, what is going on? Okay. And so it's not the worker's fault. You have an unbalanced process. Different tasks take different times. And that makes one task a bottleneck. It creates blocking and starvation. task A cannot help but have a 40% utilization. So it's not task A's fault. Either you find a way to move some of task C job to task B, some of task B's job to task A. Maybe you like balance it out, right? And everything takes 3 minutes per unit, and then everybody will have the same utilization. But unless you balance it out in an unbalanced task, this is what's going to happen. Not everybody is going to have a very high utilization. Okay. So now that you understand blocking and starvation, you understand why the utilization is 40% in task A, 80% somewhere, 100% somewhere, and so on. And the overall utilization for the whole process was 70% as we calculated before. So some managers might look at a metric, the overall utilization of their operation, and say, oh my God, my operation has a resource or worker utilization of 70%. That's terrible. I need to increase this utilization. People need to work so they earn their pay. So a manager might go to all the workers and say, I don't care what is this starvation blocking you talk about. You just have to keep on working. Well, what's that going to do? If every task that's not a bottleneck continues to work all out, well, after the bottleneck tasks which are stuff, they don't have stuff to work on, right? So they're going to just look busy and do nothing because they have nothing to work on all the time. Sometimes they have things to work on. But the task before the bottleneck, they're just going to increase WIP. They're going to work all out at their max pace and just keep adding to the pile of WIP. Okay, so utilization for non-bottleneck workers will increase, especially those before the bottleneck, but it will just create more WIP. You're not going to get more output at the end of the process. At the end of the process, you're still going to get output is limited by the bottleneck, but you just get a lot of WIP between stages. Process output will not change as is determined by the bottleneck. High WIP, creating a lot of WIP between tasks, is not good. It increases cost without increasing the output of the process. So you're still outputting the same 12 units per hour, but your cost went up because you have such high WIP, and so you're less profitable now. You shot your profitability down just because you couldn't handle some workers having low utilization, where it was not their fault, it was the fault of the way the process was designed. Okay. So high WIP has cost. You might ask why. How can WIP have cost? Just WIP, right? It's just work in process inventory. Remember what throughput time was. Throughput time is all the cycle times plus all the waiting times. The more WIP there is between two stages, the more the waiting time between two stages. So if you increase WIP, you increase throughput time. Okay? Why do we care? We care because if you are making something for a customer, throughput time is how long you need to make something for the customer to handle the customer order. So if you are a supplier supplying something to a buyer company, let's say you're supplying brakes to GM. You build brakes to supply to GM. If your throughput time in your factory goes up, your lead time that you can promise GM will go up. Because now when you start a new batch of brakes or a new production order, it's going to take longer to go through the system because you have all that WIP blocking things up and things are going to wait in the WIP piles longer. And so you'll have GM will say, okay, I need this next week. And you'll say, oh, no, my throughput time is 2 months. I can't offer you a lead time less than 2 months. And so GM might be unhappy with you and say, you take too long, I'll go to some other supplier. So how long throughput times means the longer it takes to process new customer orders, which means the lead time you can promise the customer is longer, which means less customer satisfaction. So WIP has a cost. WIP ties up working capital because when you're using up material and energy and worker hours to produce WIP, the value of the WIP inventory is higher. The more labor hours, the more material goes into it. And so you have this working capital tied up in this WIP inventory, and working capital costs money. You're financing the working capital at 8% interest, 6% interest, whatever the interest rate is, or your financing rates are. And so you are paying that much money, financing charge on the value of your WIP inventory. So if your WIP inventory goes up, your financing charges go up. That's a direct cost. WIP uses space. Maybe you built up so much WIP, now you need to create space or shelves to store product. You need to buy shelving or carts or some sort of storage system for the WIP. That costs money. WIP increases double handling. If you had zero WIP, station A just gives the stuff to station B. Maybe there's a conveyor between them. Now that you have to WIP, you have to pick up the output of station A, put it in some shelving, and then when station B actually needs it, go back to the shelving, pick it up, take it to station B. You're doing double handling. Once from station A to the storage, then storage to station B. That's twice the amount of labor to handle. Your material handling costs go up. Working capital costs go up, material handling costs go up, space requirements go up, storage system requirements go up, lead time you can promise the customer goes up. WIP has a lot of cost. Okay. And why did we create all this WIP? Because we couldn't live with the fact that some workers are going to have less than 100% utilization. Because you have an imbalanced process. Not every process step takes the same amount of time. So high utilization, this is a very important lesson. High utilization does not necessarily translate to higher cost efficiency. It can, but not necessarily. When can it translate to higher cost efficiency? For highly balanced processes where each task takes exactly the same time, such as highly balanced assembly lines, where you have a takt time in an assembly line. So every 30 seconds, every station is done. Every station just takes 30 seconds to do their job, or 1 minute. So the assembly line has a pace. It's a paced assembly line. Every 60 seconds or 30 seconds or 2 minutes, things move from one station to the next. So it's running at that same pace. And you have divided the work so that each station's work takes exactly the 30 seconds or 60 seconds, whatever the takt time is. Takt time is another word for cycle time. Cycle time is. Right? Now, sometimes it's just not possible. Sometimes it's not possible to split up work so that all the steps take equal time. Imagine you're in a car assembly line and you have a paint shop. Okay? Maybe putting on wheels of the car takes 2 minutes, but painting the whole car takes 30 minutes or 20 minutes. Okay? You can't split up the painting because it happens with highly specialized equipment, robotic arms and whatnot. You can't tell the person putting on the tire, hey, you paint some of the car, and maybe the person in a step before you paint some of the car, right? Because the painting is a highly mechanized robotic process that can't be split up. And so sometimes work can't be split up as fine as you want it to be. And so you cannot create an extremely balanced process. When you cannot create an extremely balanced process, you have imbalanced cycle times. You're going to have blocking and starvation. You're going to have lower utilizations. And trying to max utilization is going to cost you more because of high WIP. And this is something that many people don't understand. And it just goes against their nature. They can't see people idle. They want to make everybody work all out, and they end up increasing the cost for the company. Okay. So hopefully now after this lecture, you will not make that mistake. Reducing a bottleneck's task time will raise utilization while increasing output. So that is the way to go. Not just make the people who have idle time work more and just make WIP. You attack the bottleneck. Okay, an amazing book, which really shows you real life type examples on how to do this, is the book called The Goal by Ellie Goldratt. The Goal, T-H-E, The Goal, G-O-A-L, Goal by Ellie Goldratt. You can go online and buy that book. It's not very expensive. And you can read it and you can understand these ideas. They explain these ideas very well. And this idea of attacking the bottleneck and not just maxing utilization to build WIP, all of this are the central themes and ideas of what we call the theory of constraints. And the book The Goal is all about theory of constraints. So if you want to understand this better, or you understood it but you want to find an example to show it to other people, to explain to your boss, get the book The Goal. This one slide is kind of summarizing the lessons from that book, but there's an awesome book because in the book, the manager doesn't understand this. And slowly through trying different things, the managers come to this realization. So it walks you through the thinking of a normal person on how this doesn't feel right, but eventually they come to the realization and they see the proof for themselves that this is correct. And that's a very nice journey to go through. So I highly recommend you read the book, The Goal, because it's such an important lesson for operations managers. So this often happens, right? There's some people who say, well, the company's under trouble. We all need to work hard. The CEO gives this motivational speech. But no matter what you do in your role, you try to do your best. You try to work fast and accurately. Nothing improves in the company. Well, if you are doing more work and harder work and better work and nothing is improving in the company, that means you're not the bottleneck. Okay? So relax. You have to, well, maybe not relax, but find the bottleneck and then go find a way to relieve the bottleneck, to improve the bottleneck. Okay? This is one of the main insights of theory of constraints, that going around the whole company and telling everybody to work faster and just produce more is not a great idea. You're just going to build whip. Just go identify the bottleneck first and work on the bottleneck. The theory of constraints focuses your process improvement efforts. You don't need to improve the whole company at the same time. You want to go to the bottleneck, improve the bottleneck, find the next bottleneck. Because whenever you improve the bottleneck will move. Something else will become the bottleneck. Go find the next bottleneck, improve that. So you go in a systematic way in improving. Okay. Let's look at another life lesson. Okay. So some bosses think to be a boss, to be a manager, is just to go around and just make sure everybody's working hard. Everybody shows up on time. Some managers, their whole idea of management is, who showed up on time, who was like 30 seconds late, and then who's staying, 30 minutes over and working hard. And they just go around looking over people's shoulders and who's working hard. And that, they think, is all what management is about. Well, that could be a small part of management. That may not even be a good way of managing people. But that's certainly not what management is about. Okay, so this boss is kind of hiding in plants, trying to find workers which are idle, and says, I'm a good boss. I hunt idle workers. Hi, I just caught one. This worker, was doing something else. They were idle, right? And theory of constraints says, unless you have a completely balanced process, you're going to have idle time at non-bottleneck stages. And so if you just go around whacking people on the head for having a little bit of idle time, all you're going to do is increase work in process inventory. Or if there are people are starved for work, that the work didn't come to them from the previous station, they're just going to do LBDN. They're going to look busy and do nothing because that's all they can do. There's nothing else they can do, right? So they just look busy, do nothing. And if you don't understand this idea of bottlenecks, this idea of blocking and starvation, you're going to be a terrible boss. Most likely. Okay. Some people work out these ideas on their own, they observe and they learn, but these are key ideas that I want you to keep with you from this course, which is why this is one of the most important lectures in this entire course. Okay, so look busy, do nothing. Just pretend you're working, but you can't really work because you're not the bottleneck and there's going to be idle time for you. Okay. Now, the last thing I want to talk about is, in our process diagram so far, we didn't really put in a lot of inventory buffers or work in process buffers. Sometimes it makes sense to have inventory buffers, okay? And let's talk about that. I mentioned, just building WIP for no reason is just going to increase your costs and not increase your output. So it's not a good idea. But sometimes you need some inventory buffers, and when do you need them and where to put them in your process. An inventory buffer is a deliberate stock of items placed between two process stages. In service processes, waiting customers are work in process inventory, and they serve the same purpose. Okay. Inventory buffers or customer waiting areas decouple the activities so that disruptions in one activity do not immediately starve the downstream processes. Let's say there's some starvation happening because you have an imbalanced process, but let's say one of the workstations, the employee wants to take a bathroom break, or they just fall down and they're hurt and they need to be off the work for a little bit, and you have to get a replacement worker in, things like that, then these small disruptions don't increase the starvation down the line and don't reduce your output. So you can have some inventory buffer if you do have issues where the output of a process step or a workstation is variable. And if the output is variable, it's not always 10 units per hour, sometimes it's 8, sometimes it's 11. If it's variable, you want to protect the downstream steps from this variability. You want to have them continue to work as much as they can. You can have a little bit of an inventory buffer, not too big, but some work in process inventory. So when the output of this station falls from 10 to 8, it doesn't slow down everybody else. Everybody else can still continue to work at 10 units per hour, and then maybe this one catches up. Maybe does 11 for a little bit to catch up and so on, right? Or you just work extra at the end of the shift, some overtime, to rebuild the inventory buffer that you used up in the day. So you can decouple two tasks, especially if one of them is variable. Takes sometimes a little bit more, sometimes a little bit less time, then you can put an inventory buffer between them. What are the trade-offs? Inventory buffers improve reliability. So, Murphy's Law, something will go wrong if it can go wrong. So some accident happens or a worker is absent, all these sort of things happen in your production process or your process. If you have some work in process inventory that can buffer you against these disruptions in the process. Right? So it increases the reliability. At the end, your end customer doesn't see a disruption. Even though there's a disruption in step B, at the output of step B, there's no disruption because there was some work in process inventory between each stage where that smoothed over the disruption, the work in process inventory. So that's the benefit, that it improves the reliability of your output at the end. But it increases throughput time. Any WIP, even 1 unit of WIP is going to increase your throughput time and it's going to increase your holding costs. So how much is the benefit versus the cost? You don't want too much WIP because then it's going to cost too much. But some amount of WIP to pay, increase your throughput time a little bit, pay a little bit holding costs, but it gives you more reliability in your output, may be worth it. A key example is in healthcare. The doctors are often the most expensive resource in a healthcare setting. And so you don't want your most expensive resource to be sitting idle, because any amount of time the doctor spent being idle is time you're paying them, but they're not producing any output for the system which you can bill. So often you'll see in clinics, they'll have 4 or 5 waiting rooms which are filled up by patients. And when the doctor is done by one patient, goes to the next, the doctor never has to wait for the next patient to arrive. Patient is already buffered or put in a WIP inventory in a waiting room. So when you buffer patients in waiting room, you are getting the high resource utilization of the doctor, which is efficient in terms of from a money perspective, because the more patients the doctor sees, the less idle time the doctor has, the more money the healthcare facility can recoup by billing for those patients, right? So you're able to utilize your doctor, the expensive resource, better by having these waiting rooms. But what's the cost? Well, you have to have those waiting rooms for a bigger clinic. There's a cost of space, right? And the customer experience, the patient experience will decrease because now the patient's throughput time in the system is increased because they're waiting in that room before for the doctor to arrive. So their total time spent in the system goes up. As long as you don't increase the waiting time too much, and you don't need a whole lot of expensive space for those rooms, it is usually justified to have some work in process buffer, not queue up like 30 patients in waiting rooms, but like 3, 4, 5. So it's a worthwhile trade-off so that the doctor is protected against, some patients are arrive late, some patients will arrive, will walk more slowly, will need to use the bathroom, right? So there's all this variability in the arrival process to the doctor. So you put a buffer there to protect the doctor from that variability. The doctor is always working at 100% utilization because the doctor is your most expensive resource. So you see that done in healthcare a lot. So here's some guidelines on placing inventory buffers, which location and the reason. So before bottlenecks, now the bottleneck is already your slowest step. If the bottleneck is starved for work, that's really bad because the bottleneck is already limiting your production. And if the bottleneck is waiting for product, that's just hurting your production even more. You might ask, how can the bottleneck be stopped? Bottleneck is the slowest unit, the slowest piece of your production or your process. How can the bottleneck ever be stopped? Because of variability in the system. Okay, the worker before, this is the bottleneck, the worker before had an important phone call and had to step away for 5 minutes. And now the bottleneck is stopped for work. Ideally, if the worker before never had to take that unintended break, it wouldn't be stopped for work. Sometimes it's as simple as you have to give your worker breaks, lunch break, rest break, right? And so if you have no WIP before the bottleneck, whenever the workers before, in any of the steps before the bottleneck take a break, bottleneck is stopped for work. So how do you handle that? You have just enough WIP that their breaks, when they go on a break, the bottleneck uses the WIP to continue working. And when they come back, they can rebuild the WIP because they work faster than the bottleneck. So you put some little bit of WIP before the bottleneck to make sure the bottleneck never stops working, because the bottleneck is already limiting your output. If the bottleneck stops working, your output will be even more limited. So you'll often see a little bit of WIP put, WIP inventory, an inventory buffer put just before the bottleneck. Before expensive steps or resources, like the doctor example I told you, you often want to put a little bit of WIP before a very expensive step or resource so that that expensive resource or step continues to happen and is protected by variability in the system before that. Variability like accidents, a worker taking a break, or a worker being absent and a makeup worker being slowed at the task. All sorts of things happen in real life that can reduce the output of the steps before temporarily. And then if you have a WIP that protects this expensive step or the bottleneck step from being slowed down by the tasks before it. After unreliable stations or low yield steps. So if you have a step, okay, on average it has a 90% yield. So you design your whole process on 90% yield, but there's variability and sometimes the yield is only 80%. So it only, instead of 90 pieces in that hour, it only produced 80 pieces in that hour. There's more defects. Because there was a raw material issue or something else happened. Now the downstream task is going to be stopped because instead of the 90 they were expecting, they only got 80 units to work on, right? So again, you after unreliable station, you can have some WIP builds up, maybe build up the WIP with some overtime, and then if the WIP goes down, you again schedule some overtime to rebuild it up. But that WIP ensures that on a bad day, on a day when you have low yields, the rest of the process doesn't have to slow down and continues to work. So you'll often see some WIP inventory being used after unreliable stations or steps in processing where the yield is variable and sometimes you get low yield output. At diverging points. So this one is, let's say you have a step after which this unit is going to go to two different steps. So let's say you cut the wood planks, and now these wood planks that you just cut up are going to go on one side to make legs and on the other side to make tabletops, and then tabletops and legs will come together to make a table. Okay. So what if the tabletop part of the process, okay, runs faster than this other process just makes the legs. So you have this wood going to two different areas. One, they have different speeds of working, okay, and they may even have some variability in their work. Maybe making legs is a complex process. If you get a bad piece of wood or some other things in the wood, they have to be fixed before you can make the leg, things like that. So sometimes people get some WIP here because let's say the tabletop process is working a little bit faster than the leg process because of some defects in the wood or something. It has extra wood to take and it will continue to work. Okay. This is not that important because at the end, the tabletop and the legs have to come together to make the final unit. So even if this one of the ones works faster than the other, because it continues to work faster for longer because of the WIP, it's not really going to help that much because at the end of the day, you can't process tabletop without the legs. Okay, but sometimes it never comes back together. You're using wood to make two different products. So here you're making, on the right, you're making maybe desks for offices and schools, and on the left you're making some custom furniture, and then you might want some buffer because a big order comes in for school desks, and this unit is going to run faster or for longer today than it was running before because of the difference in order. Before it was just producing desks for offices, now it's got a big order from a school, and so if you didn't have any WIP, this part of the process, which is making desks for schools, may have to wait a long time for you to get all the wood cut up, or may have to slow down, maybe starved because of that. So sometimes when you have a process step feeding different processes which work at different speeds, or this variability in their work requirements from day to day, depending on the orders they get, you may put some WIP there to decouple these steps, to not have them dependent upon the speed of this step. Often, at the end, no, I forgot. At converging points, I forgot this one. So at diverging points is when you diverge. Converging points is when different pieces come together and they have to be assembled. So if you remember the example we did where we had to, in the very beginning, we got different pieces of a chair and we assembled it. We had WIP right there. So it's all the way back, but I want to show you this important idea. We're almost there. Right here. Okay. Notice you have the seat, the front legs, the back legs coming together, and you put WIP right here, chair components before the assembly. Why? Because if you didn't have any WIP, and let's say it took longer to make the back and fashion the back legs than the other two steps, you might have more front legs than back legs, and then the assembly can't proceed at its regular pace because it has to wait for the back legs for those chairs that are missing the back legs, because you got front legs, were easier to produce, and you got more of those and you got less of those. So if you have some WIP, it decouples these component manufacturing from the assemblies. You often see that where you decouple component manufacturing from the assembly step with a little bit of WIP, so that if certain components, there's variability in their production, or there's a bad batch with lots of defects, or one component that's required is slower to produce, maybe every few weeks you do some extra shift to build up some WIP, then you use that WIP later on. All of these things you can do to decouple the assembly from variability in component processing, so that even if there's issues with one of the components, the assembly process can continue to work. Okay. Obviously, you don't want huge amounts of WIP, but some WIP can be beneficial. It's called a converging point, where different paths in the process converge, and now you're going to have just one path forward. And this here is a diverging point, where you have WIP of wood to feed these different processes which work at different speeds. Okay, so converging and diverging points, these 2 points here are cases where people will often add a little bit of WIP. Inventory, just to decouple the steps and make sure that variability in one does not affect and starve the next step. Okay, so at the very end of a process, when you have finished goods, what if the demand is variable? You predict that you need to produce, let's say, 100 units per day on average, right? But let's say on one day the demand goes up to 120 and you only set up your process to produce 100 units per day. What did you on that day? Do you just leave 20 units of demand? Well, if you have a little bit of finished goods inventory, a little bit of inventory at the end, you can eat into the inventory on days where the demand exceeds your production. And on days where demand is below your production, you build that inventory back up. So you have a little bit of safety stock at the end, or finished goods inventory. So at the very end of the process, sometimes it makes sense to have a little bit of safety stock to handle demand variability. And at the very start of the process, again, where raw materials come in or components come into your factory, you may want to have a little bit of a little bit of inventory there of raw materials or components, because what if shipments are delayed? Okay, if you notice the world today, there's a lot of disruptions happening in supply chain. A ship had an accident in the waters, or some conflict of war broke out in your ship that's bringing the components, has to take a longer route around Africa or something, and it's going to be 2 weeks late or a month late, right? So if you have no inventory of inputs at the start of your process, then your process is going to get disrupted again and again by any disruptions outside your factory of the stuff coming in. Strike at a port, truck accident, port accident, any such thing can disrupt your production process. So often companies will have some inventory at the very beginning of the production process, some inventory at the very end. The beginning inventory buffers them from supply disruptions. The inventory at the end protects them from demand variability, because when the demand goes up a little bit, they can still meet the demand through the finished goods inventory. Okay. So these are some guidelines about thinking about where to produce inventory buffers. Again, remember, inventories, especially work in process inventory, is going to increase your throughput time. Finished goods inventory will not increase your throughput time, but the work in process inventory will increase your throughput time. All inventory increases your storage cost, your working capital requirements, and entire cost. Okay, so we're gonna so that's it for this part, and we'll continue on with discussing Little's law and then doing some more examples in the next part.